Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics 2. In this lecture, we will start the inverse Laplace transform. In the previous lecture, we studied about the Laplace transform and its property. Before starting inverse Laplace transform, we recall the Laplace transformation. Here, we know that Laplace of ft, that is denoted as L of ft, equal to integration 0 to infinity e raised to minus st ft dt, and answer is in terms of s. That means we have some function of s which is phi of s or f bar s. That means we have a Laplace of ft is equal to phi of s. Now, what is a inverse Laplace transform? So if Laplace of ft is phi of s, then we can say that inverse Laplace of phi of s is ft. That means we can convert function of t into the function of s using the improper integration 0 to infinity e raised to minus st ft dt. In this case, we can say that ft is a inverse Laplace of function of s, which is denoted as phi of s. Now we will see some concept of inverse Laplace transform. Here we can see that Laplace of e raised to bt is 1 upon s minus b. Then we can say that inverse Laplace of s 1 upon s minus b is e raised to bt. Similarly, we know that Laplace of e raised to minus bt is 1 upon s plus b. Then inverse Laplace of 1 upon s plus b will be e raised to minus bt. That means this is the exactly reverse process of Laplace transformation. Here Laplace of 1 is 1 by s, then inverse Laplace of 1 by s is 1, and the Laplace of cos hyperbolic at is s upon s square minus a square, then inverse Laplace of s upon s square minus a square is cos a t. Now we have some more formula on inverse Laplace are these. Here Laplace of cos at is s upon s square plus a square. Then we can say that inverse Laplace of s upon s square plus a square will be cos a t. As we know that Laplace of sin a t is a upon s square plus a square. That implies we can say that inverse Laplace of a upon s square plus a square is sin a t. But sometime we have a 1 on left hand side numerator, which is like L inverse 1 upon s square plus a square. In this case, we divide the sin a t by a. That means L inverse of 1 upon s square plus a square will be sin a t by a. Now, sin hyperbolic at is a upon s square minus a square. Then L inverse of a upon s square minus a square is sin hyperbolic at. When we have a 1 on left hand side in place of a, then L inverse of 1 upon s square minus a square will be sin hyperbolic at divided by a. Now we know the Laplace of t raised to n is gamma of n plus 1 upon s raised to n plus 1. In this case, we have a L inverse of gamma of n plus 1 by s raised to n plus 1 equal to t raised to n. And this formula is also applicable as L inverse of 1 upon s raised to n, that is equal to t raised to n minus 1 upon gamma of n. Here we divide the gamma on right hand side. Now we will see the first shifting property in the inverse Laplace transform. Here our question is L inverse s plus b upon s square s plus b whole square minus a square. Here our question is, it is a Laplace of which function? Here s is replaced by s plus b in our question. So we can rewrite our question as L inverse s upon s square minus a square, where s is replaced by s plus b. Here L inverse of s upon s square minus a square is a Laplace of cos hyperbolic at, and in our question s is replaced by s plus b. So we have to multiply cos hyperbolic at with e raised to minus bt. Then our final answer is L inverse of s plus b upon s plus b whole square, minus a square equal to e raised to minus bt cos hyperbolic at. Similarly, our question is L inverse a upon s minus b whole square minus a square. Then it can be rewritten as L inverse a upon s square minus a square, where s is replaced by s minus b. Then our final answer is e raised to bt sin hyperbolic at, because L inverse of a upon s square minus a square is a Laplace of cos sin hyperbolic at, and s is replaced by s plus b everywhere in our question. So we have to multiply sin hyperbolic at with e raised to bt, which is our first shifting property of the Laplace. Now the next formula is L inverse s minus b upon s minus b whole square plus a square. Here everywhere s is replaced by s minus b. That means L inverse s upon s square plus a square, where s is replaced by s minus b. Here we know that L inverse s upon s square plus a square is a Laplace of cos at, and s is replaced by s minus b. So we multiply cos at with e raised to bt in the inverse Laplace transform. Now if our term is a upon s plus b whole square plus a square, here s is replaced by s plus b, and we know that L inverse of a upon s square plus a square is a Laplace of sin at, and s is replaced by s plus b. So we multiply sin at with e raised to minus bt, because s is replaced by s plus b. When s is replaced by s plus b in our whole question, then we have to multiply our inverse Laplace by e raised to minus bt, because it is a first shifting property in the Laplace transform. Now our next term is L inverse of 1 upon s minus a raised to n. Here s is replaced by s minus a, so it can be rewritten as L inverse of 1 upon s raised to n, where s is replaced by s minus a in the original question. Now according to the first shifting property, we multiply our function t raised to n minus 1 upon gamma n with e raised to at, because here s is replaced by s minus a in the inverse Laplace transform. Now we will see the examples of inverse Laplace transform. These are the some examples of inverse Laplace transform. Now our question is in terms of s, and we have to find our answer in terms of t, because when we are take the Laplace, we go to the t variable to s variable, and when we are taking the inverse Laplace, we go to the s variable to t variable. Now we will solve the first question. Our first question is phi of s is s upon s square minus 9 plus 1 upon s raised to 5 minus 4 upon s square plus 8. Let us see how to solve this question. Here ft equal to inverse Laplace of phi of s, where phi of s is given in the question L inverse of s upon s square minus 9. It is a Laplace of some function. We separate the inverse Laplace here, then we get the L inverse of s raised to 5 in the second term, and finally minus 4 common, then we get L inverse of 1 upon s square plus 8. Here 8 can be written as 2 root 2 square. Now inverse Laplace of s upon s square plus minus 9 is cos hyperbolic 3t, plus inverse Laplace of 1 upon t raised to 5 is t raised to 4 upon gamma 5, and gamma 5 can be converted into the factorial form, and finally last term is Laplace of sin t, so it is sin 2 root 2 t upon 2 root 2. Now we can cancel 2 here with 4, then finally we get cos hyperbolic 3t plus t raised to 4, and that will be 4 factorial, because gamma 5 is 4 factorial, minus 2 sine 2 root 2 t upon root 2. And now we can cancel 2 with root 2. Then now ft will be cos hyperbolic 3t plus t raised to 4 upon 4 factorial minus root 2 sine 2 root 2 t. That is our ft. So finally our answer is cos hyperbolic 3t plus t raised to 4 by 4 factorial minus root 2 sine 2 root 2 t. Now we will solve the second example, which is phi of s equal to s upon s square minus 5s plus 6. Here we can't see the directly formula of any Laplace, but we can factorize our denominator. Let us see how to solve our question. S upon s square minus 5s plus 6. Here ft equal to L inverse of phi of s, where phi of s is s upon s square minus 5s plus 6. Now we can rewrite our denominator as a factor s minus 2 and s minus 3. These are the factor of s square minus 5s plus 6. Now we apply the partial fraction method to solve this type of equations. Here L inverse of a upon s minus 2 plus b upon s minus 3, which is the partial fraction method we already studied in the 12th science standard. Now we can rewrite our ft as L in a times L inverse 1 upon s minus 2, which is a Laplace of someone, plus b into inverse Laplace of 1 upon s minus 3, and it is also a Laplace of some function. That is a, it is first term is Laplace of e raised to 2t and b e raised to 3t. Here we have put the inverse Laplace of 1 upon s minus 2 and 1 upon s minus 3. Now we find a and b by partial fraction method. Here s upon s minus 2 s minus 3 equal to a upon s minus 2 plus b upon s minus 3, which is already written in the starting of the example, and that can be written as s equal to a into s minus 3 and plus b into s minus 2. Now we put the some values of s and find the a and b by partial fraction method. Put s equal to 3 to find b. We get 3 equal to b. Put s equal to 2. That implies we get 2 equal to a into minus 1 plus b into 0. That implies a equal to minus 2. So we have a value b equal to 3 and a equal to minus 2. Therefore L inverse s upon s square minus 5s plus 6 equal to a e raised to 2t plus b e raised to 3t, that is equal to, put the value of a and b, then 3 e raised to 3t minus 2 e raised to 2t, which is our answer f of t. So our answer is 3 e raised to 3t minus 2 e raised to 2t. Now our third question is s upon s square plus 6s plus 13. In this question we can't factorize denominator. Here we have to apply the some another trick to solve this example. Here ft equal to L inverse of phi of s, and phi of s is s upon s square plus 6s plus 13, and that can be rewrite as s upon s square plus 6s plus 9 plus 4. Here we rewrite 13 as 9 plus 4 because we get the perfect square here, s square plus 6s plus 9. So L inverse s upon s plus 3 whole square, which is a perfect square of s square plus 6s plus 9 plus 4 in our inverse Laplace transform. Now we have a s plus 3 in denominator. We have to arrange the s plus 3 in numerator. So we get L inverse s plus 3 minus 3 upon s plus 3 whole square plus 4. That is our L inverse of some function here that can be written as s plus 3 upon s plus 3 whole square plus 4 minus 3 L inverse of 1 upon s plus 3 whole square plus 4. Here we can observe that each term contains s plus 3. So that is a first shifting property in inverse Laplace transform because we already replaced s by s plus 3 in every term. Now we see how we apply the first shifting property here. Here this term can be written as e raised to minus 3t because s is replaced by s plus 3 everywhere. L inverse of now s upon s square plus 4, which is a Laplace of cos 2t minus 3 L inverse of 1 upon s square plus 4, which is a Laplace of sin 2t divided by 2. This is first shifting property in inverse Laplace transform because in our question s is replaced by s plus 3 everywhere. Now our final answer is e raised to minus 3t into cos 2t minus 3 sin 2t divided by 2. So our final answer can be written as e raised to minus 3t divided by 2 into 2 cos 2t minus 3 sin 2t. Now we will see another example. Here L inverse of phi of s is L inverse of s upon s minus 1 whole square. Here we have a s minus 1 whole square in the denominator, but numerator contains only s. So first of all we have to arrange s minus 1 in the numerator part. So it can be rewrite as L inverse s minus 1 plus s1 upon s minus 1 the whole square. Now we separate the denominator and get L inverse s minus 1 upon s minus 1 whole square plus 1 upon s minus 1 whole square. In this case we cancel the s minus 1 and we get 1 upon s minus 1 plus 1 upon s minus 1 whole square. Here we can see that both the terms contains the s minus 1. So we are applying here again first shifting property like this. Here e raised to t into L inverse of s minus 1 replaced by now s, because we already multiply with e raised to t. So L inverse of 1 upon s minus s plus 1 upon s square. Now we know the inverse Laplace of 1 upon s is 1 and inverse Laplace of 1 upon s square is t. So we can directly write down the solution as inverse Laplace of s upon s minus 1 whole square equal to t into 1 plus t. So here in the first example we directly apply the inverse Laplace formula. In the second example we are applied the partial fraction method. In the third example, first of all we convert our denominator into the perfect square form and then we applied the first shifting property. In the last example we directly apply the first shifting property. Now in the next lecture, we will discuss about the properties of inverse Laplace transform. Thank you very much.